Hello, everyone. So today what we're going to work on is we're going to focus on chapter 8, which is chemical bonding. And largely what we're going to do is we're going to talk about drawing Lewis structures. And so that's going to be the main sort of objective for what we're doing today in this video lecture. So let's begin. And so I will start by sharing my screen. And the screen now is shared. And then we go to our lecture slides. And here we go. All right, so this is where we are going to start for the day. And so we're going to talk about how to write Lewis structures. So the way you write Lewis structures is you're going to sum the valence electrons from all the atoms. That's the first thing you're going to do. So I'm going to go over the procedure, then I'll demonstrate actual examples for how to do this. But step one, sum the valence electrons from all the atoms. Question is, how do we know what the number of valence electrons are for each atom? So if you go to then the periodic table, you can then notice that hydrogen is in the first column. So it has one valence electron. So anything in this column here has one valence electron. Anything in this column here has two valence electrons. We skip over here, go to the third column. These elements have three valence electrons. These ones have four valence electrons, five valence electrons, six valence electrons, seven valence electrons. And then finally, for the noble gases, we then have eight valence electrons. So that's how you know it, because you just count across the periodic table: one, two, three, four, five, six, seven, eight. Those are the number of valence electrons you have. And so when we do that, that's step number one. So then what we're going to do is going to use a pair of electrons to form a bond between each pair of bound atoms. Step three, you're going to then arrange the remaining elements to satisfy the duet rule for hydrogen and the octet rule for second row elements. Then what you want to do is see if you used up all the valence electrons in step one. Okay, so there's a lot of rules you got to follow, which is you got to make sure that you're using the correct number of valence electrons. Then you need to make sure that the atoms that need duets have duets, and the atoms that need octets are going to then have octets. And so we'll demonstrate that with the Lewis structure for water. So I'm going to just show you what this one looks like. And so what you have here is the Lewis structure for water. Okay. And so what the Lewis structure for water is it looks something like this. And so you have an oxygen atom, and then you then have a hydrogen atom over here, and then you got another hydrogen atom over here. And what you'll notice is when you have two electrons that are shared between two atoms, that is our way of communicating a chemical bond. So if you go to the top line up here, two shared electrons represents a bond. And then if you have non-bonding electrons, those are what are then called a lone pair. So you'll notice in the Lewis structure of water, we have oxygen in the center here, and it's got then one lone pair at top. It's got a second lone pair at the bottom. So those lone pairs are exclusively sitting on oxygen. But then oxygen also has one bonding pair that is shared between oxygen and hydrogen. And then it has another bonding pair that's shared between oxygen and the second hydrogen atom. Okay. And so those are going to then be all the total of electrons that we're using. And if you add all these electrons up, you notice that we have two electrons associated with hydrogen, one and two. And then on the other hydrogen, we have two electrons associated, one and two. And so that's what we mean by hydrogen following the duet rule. So hydrogen can only have two electrons associated with it. Then oxygen is going to then have a total of eight electrons associated with it. It's going to have one, two, three, four, five, six, seven, eight electrons associated with it. Okay. And so this is going to follow the duet rule and the octet rule. So hydrogen has a duet, and then oxygen has an octet. But you'll notice here that the two electrons count for both oxygen and for hydrogen because they are shared between the two atoms. So they can count for both atoms. You'll notice that the lone pairs only count for oxygen because they're sitting only on the oxygen atom. So in the introductory examples that we will talk about, hydrogen will have a duet, And then other second row elements will then have up to an octet, which is 8 electrons. And then we're going to break that a little bit later and show that if you go to the third row elements, they can have then more than 8 electrons. But just for starters, hydrogen, 2 electrons, and then the other atoms we'll look at will then have a total of 8 electrons. So, looking back to our little picture we have here, or our outline, the first step is you got to sum the valence electrons from all the atoms. So how the heck do we know how many valence electrons we have? So if you go to the periodic table, you notice that we have 2 hydrogen atoms. So each hydrogen atom is going to have 1 valence electron. So that means you get 2 valence electrons from the 2 hydrogen atoms. Then if you look at oxygen, you see oxygen is in column number 1, 2, 3, 4, 5, 6. So you see oxygen is in column number 6. So oxygen has 6 valence electrons. We then have 1 valence electron from each of the 2 hydrogen atoms. 6 plus 2 gives us 8. That's the number of electrons we need to use. And so when you then go to your structure and you look over here, you then count up all the electrons and you get 2, 4, 6, and 8. And so we use all 8 electrons. Hydrogen has a duet, hydrogen has a duet, and then oxygen has a 2, 4, 6, 8, has an octet. So this is good, and this is the correct Lewis structure for water. All right, so one thing to point out to you is most technically speaking, a Lewis dot structure only uses dots. Okay, and so this is what's called then a Lewis dot structure because the electrons are only shown using dots. Okay, so 1 dot equals 1 electron. Um, People typically don't write all the dots out like that. And what people will commonly do is they will represent a bonding pair of electrons as a line. And so you'll notice that these 2 electrons here and these 2 electrons here then get replaced with a line. And so you can see oxygen still has a octet because it's 2, 4, and then 6, and then 8. And so each line counts as 2 electrons for the atom, and then each dot counts as 1 electron for the atom. And then we'll talk about geometry later, but we know that water has a bent molecular geometry. So conventionally, people will try to write the Lewis structure in a way that best communicates what the true geometry of the molecule is. We'll save that discussion for later in the chapter. Okay, so now what we're gonna do is we're gonna get a practice question with this. Okay, so first thing we're gonna do is we are gonna draw the Lewis structure for CCl4 or carbon tetrachloride. So for carbon tetrachloride, the way it's gonna work is pretty much like this. And so you have carbon, okay? And we know that we have 1 carbon atom, and we know that carbon is in the fourth column of the periodic table. 1, 2, 3, and 4. So here's carbon in the fourth column of the periodic table. So we have 1 carbon atom. It brings 4 electrons to the party. And so therefore we have a total of 4 valence electrons from carbon. Next, we move on to chlorine. We have 4 chlorine atoms, okay? And then we know that each chlorine atom is going to bring to the party 1, 2, 3, 4, 5, 6, and 7. So chlorine's in the seventh column here. So each chlorine atom is going to bring 7 electrons to the party. And so we then do times the 7 electrons. And then that's going to then give us a number of 28 electrons from then chlorine. Okay. Then if you add all of those electrons together, you get the total is going to be equal to then 32 electrons. Right? So that is what we get. Okay. So for this exercise here, we got to use a total of 32 electrons. And that comes from the molecular formula of what we're dealing with here. And so here we're doing it for CCl4. Okay, and so that's what we're doing here. So let's get started. And let's change the font because I don't like Times New Roman. So we'll change it. All right, there you go. So start with the central atom. Okay, start with central atom. So one way to do this is the central atom usually is the atom that you have maybe one of. That's not a hard rule and it doesn't work all the time, but it tends to work pretty well for introductory examples. And so we got one carbon, we have four chlorines, and so we should then have carbon be in the center atom. And so what you can do is you want to make single bonds to the center atom. So make carbon your central atom and then put the chlorines bonded to then the central atom. Okay? So you're gonna do that. And then you get something that looks like this. Okay? So we've selected carbon as the central atom. The reasons we have for that is that carbon, we have one of it, and so that's a good indicator. Also, carbon likes to form multiple bonds, and so it's usually a good contender to be something that's going to be in the center of a small molecule. Okay. We'll see other examples that will provide more depth into what we're talking about. So, what we can do here is, okay, we've made single bonds to the carbon. Now what we want to do is we want to then make sure that every atom has an octet. And so if we look at the chlorine atom, we see it only has two electrons associated with it because it has two electrons between the carbon and the chlorine. So that carbon-chlorine single bond counts for two electrons. So I need chlorine to have eight, which is an octet. So I need to do one lone pair, two lone pair, three lone pair. And when I then look at that, you're going to then notice that I have two, four, six, and then eight electrons associated with chlorine. And so chlorine has an octet, and I'm in good shape here. Then you do the same thing for the other chlorine, add those lone pairs, do it for the other chlorine, do the same thing, and then do it for then the other chlorine. Okay. So once you've done this, you can then notice now that you have four chlorine atoms and they all have an octet on them. Okay, so that's good. Then we look at carbon and we need to ask ourselves, does carbon have an octet? And so we look at carbon and it has four single bonds. It has, and each single bond counts as two electrons. So we have two, four, six, eight electrons associated with carbon. And so carbon has an octet. So what we've done here is we've satisfied a couple of the rules we have here, which is we need to make sure that carbon has an octet. We need to make sure that then chlorine has an octet. Then finally, we need to make sure that we are using a total of 32 electrons because that's what we get from this number that we did at the beginning. And so if you take a look here at each chlorine, you see it has two, four, six, eight electrons. So for one chlorine, we have eight. For the second chlorine, we then have 16. For then the third chlorine, we then get up to 24. And then when we go to the fourth chlorine, we then get up to 32 electrons. So what we can see in the structure here is that we satisfy the octet rule for carbon and chlorine, and we are using the correct number of valence electrons. And one thing just to remind us is that the electrons that we're showing here are the valence electrons, okay? So they're the ones in the outermost energy shell. We're not talking about core electrons here because it's these outer electrons that are going to be participating in the chemical bonds. So that wraps up the first question, which is carbon tetrachloride. And so you'll notice the way I drew it, it looks sort of like a cross. And I'm not intending to communicate, most perfectly what its geometry is going to look like. But if you were to look to what you would find if you maybe looked it up online or something, is you would probably find it looking something like this. So this has these wedges that are being shown, and there's something I'm going to introduce gradually as we go through the class. But essentially, remember that your carbon tetrachloride, it's a three-dimensional molecule, and this is what the actual structure of it looks like, shown here at the right. And it has this special geometry, which is then called tetrahedral, or as I like to call it, the tripod geometry. It's got one leg, two legs, three legs, and then it then has a neck. And so what the wedges are trying to communicate is that a dash wedge means that the atom is going into the plane of the board. And then the solid wedge is meant to communicate it's coming out of the plane of the board towards you. So this chlorine with the solid wedge is this chlorine atom. And this chlorine with the hashed wedge is going to then be this chlorine atom. And then you'll notice that this atom, and this atom are all in the same plane of the board. And so therefore they're just drawn with single lines. So you have this carbon chlorine bond, and then you then have this carbon chlorine bond as well. Okay, so that's our structure for carbon tetrachloride. Now we're going to do the same thing, but we're going to do it for then hydroxide anion. So for hydroxide anion, we'll change it here. So we'll do OH minus. Hydroxide anion works like this. We are going to be working with oxygen and hydrogen. Okay. And so we have one oxygen atom. And if we look up what column oxygen is in the periodic table, we see oxygen is in column 1, 2, 3, 4, 5, and 6. So oxygen is going to be in the sixth column of the periodic table. And then hydrogen is in the first column of the periodic table. So we can say that we have one oxygen, which brings 6 electrons to the party, which gives us 6 electrons. And then we have one hydrogen, which brings 1 electron to the party. And so that then brings us one valence electron from hydrogen. Okay. The important thing to notice here is that for this structure, we're doing it for OH minus. So this is hydroxide. So what this means is we have one additional electron, okay? Um, and so what this means here is we are going to then add one more electron, okay? That one electron is going to then be because we have OH minus. And so if we add all of these electrons together, we get 6, 7, and 8. And so we then get a total of 8 valence electrons. Okay, so let's get rid of our old example. So for hydroxide, we're going to then have a total of 8 valence electrons to work with. And so then the next thing we got to do is we got to figure out the central atom. Well, we don't really have a central atom because there's only 2 atoms. And so this tells us that oxygen must be bonded to a hydrogen atom. Okay. And so you're going to get something that looks like this. Okay. So you're going to have an oxygen bonded to the hydrogen atom. Okay. Then what you're going to do is you need to make sure that everything that needs a duet has a duet, and everything that needs an octet has an octet. So you'll notice hydrogen here has 2 electrons being shared between it and oxygen. So hydrogen has the duet rule satisfied. Oxygen, you'll notice, as written, only has 2 electrons associated with it, and that's from the bonding pair with hydrogen. So oxygen does not have an octet. It only has 2 electrons associated with it right now. So we need to get that number up to 8. And so we'll then add 1 lone pair, 2 lone pair, and 3 lone pairs. Okay? And when you do that, now you're going to see that then hydroxide, or rather the oxygen in hydroxide, it's going to then have a full octet because it has 2, 4, 6, and then 8. I'll show it here. It has 2, 4, 6, and 8 electrons associated with it. So oxygen has a complete octet. This is good. So what we're gonna do here is we're almost done. So we have an octet on on oxygen, we have a duet on hydrogen, and then do we use a total of 8 electrons? And so we take the 2, the 4, the 6, and the 8. That adds up, matches to the number. We are good. So there's one final thing we need to do here. So remember that hydroxide is an anion. So what we need to do is we need to denote that this is going to have some charge associated with it. Okay. And so what you want to do is then draw little brackets, and then you then put the negative charge over there, and then you're good. Okay. And so that's how you're gonna then denote then that you have the negative charge associated with hydroxide. Okay. So at this point, we're gonna say it has a negative charge. At this point, we don't know where that negative charge is gonna go. We'll talk about the answer to that later, but you want to make sure that you put the brackets and then put the negative charge in the upper right-hand corner. Okay. So one thing just to point out to you, if you don't put the brackets with the negative charge or with the correct charge on there, that's not going to get it full points, but you'll get most of the points for getting the correct Lewis structure, but probably 1 point deducted for then not putting the bracket with the correct charge. So it's not the majority of the points. All right, so that summarizes and concludes hydroxide. Um, when the picture I have here, later on in organic chemistry, you'll learn to actually figure out where that negative charge goes. And we'll talk a little bit about that later in this class. But it turns out that the negative charge wants to sit on the oxygen atom. And if we spend a moment to sort of think about that, it does make sense to us because remember, oxygen is a lot more electronegative than hydrogen. So if you're going to have a negative charge on your on either of those two atoms, it's going to sit on the more electronegative of the two atoms. And so that's why we have that. Okay, so now we're going to do is we're going to do the same thing, but we're going to do it for a cation. And this is going to be for the hydronium ion. So if we do it for hydronium ion, we get H3O plus, and then we'll get rid of all this stuff over here. And then we have H3O plus. So we will have H3 and the O, and we'll delete the other stuff that we don't care about. Okay. All right, so H3O plus. So we have 3 hydrogen atoms. Hydrogen is in the first column of the periodic table. So each hydrogen brings to the party 1 valence electron. And that means the 3 hydrogen atoms bring a total of 3 valence electrons to the party. We go to oxygen. Oxygen, we have 1 oxygen atom, and oxygen is in the sixth column of the periodic table. And so it then brings to the party 6 valence electrons. And when you do that, you then get a total of 6 valence electrons from then the oxygen atom. Okay. So that's the number of valence electrons that we have from hydrogen and oxygen. But recall that we are talking about hydronium ion or hydronium cation. It has a positive charge, which means it has lost 1 electron. So just how with hydroxide we added 1 electron to account for the negative charge, here we need to then remove 1 electron to account for the fact that we are a cation, which has lost a negative charge. So here you're going to then subtract 1 electron. And so when you subtract the electron, then you're going to get 6 plus 3, which is going to then be your 9, minus 1, brings you then down to 8. So you're going to have a total of 8 valence electrons in your hydronium ion. Okay, that's how many you're going to have for that. So going back to where we are, let's draw this out. So which atom do you think should be the central atom? Well, we have 1 oxygen, so let's go with that. And then also hydrogen can only form 1 bond. So that doesn't make sense that hydrogen would want to be a central atom. And so you're going to write the central atom. And then what you're going to do is you're going to then draw single bonds to the other atoms. Okay, so you're going to have the hydrogen atoms form single bonds to the central atom. Okay. So you're gonna get something that looks like this, okay? And you'll notice here that hydrogen has the duet, so it's good for all three of them. And then you'll notice that oxygen does not have an octet. We'll notice it has two, four, and six electrons associated with it. So this oxygen needs an octet. And so what we're going to do is we're going to put on one lone pair of electrons. And now oxygen is going to then have the complete octet because it now has two, four, six, and eight electrons associated with it. So oxygen has an octet, the hydrogens all have a duet. Now we need to double check to make sure that we're using the same number, the eight that we have from here. And so we then add up and we got two, four, six, and eight. This matches the total number of valence electrons. We are good. However, though, just remember we're talking about a cation, so we got to put brackets around it. And then what you need to do is then designate that you then have a positive charge. And so you're going to then put the positive charge over there. And then that's going to be your completed Lewis structure for the hydronium cation. So, if you go on to what the solution is, you then get something that looks like this. And similar to the other example, um, what you'll notice here is that, actually rather not similar to the other example, you notice here that actually the oxygen is going to be a little bit electron deficient and actually has a positive charge on it. So that might sound a little interesting considering the other example, the oxygen had the negative charge on it, but here it has the positive charge on it. So later on, we will talk about something called formal charge. So that will come up probably in the next lecture that we do, and that'll explain why the formal charge, the positive one, is on the oxygen. But for the purposes of where we are now, all we're good with is just saying that there's going to be a positive charge somewhere on the hydronium cation. Okay. All right, so that concludes that question. Um, Now what we're going to do is we're going to then do it for carbon dioxide. So for carbon dioxide, let's get deleting things. So for carbon dioxide, it's going to be a carbon and oxygen. And then we're going to get rid of all this over here. Okay, so we are going to do carbon dioxide or CO2. Okay. And then we're gonna delete all this over here. All right, cool. So first thing you gotta do with everything, figure out how many valence electrons you have. So we have one carbon atom. Carbon is in the fourth column of the periodic table. So we have four valence electrons. One times four is going to be equal to four. So we have four valence electrons from then the carbon. For oxygen, we have two of them. Oxygen is in the sixth column of the periodic table. And so then 6 times 2 is going to then be a total of 12 valence electrons. And then because we have 12 from oxygen and 4 from carbon, that means we're going to have a total of 16 valence electrons for carbon dioxide. Okay? So every Lewis structure question is going to start with the same thing, which is figuring out how many valence electrons you can use. Then you're going to do the next step, which is determine the central atom. We have one carbon atom, and carbon likes to have multiple bonds. So we'll put a carbon in the center. Then what you're going to do is you want to then form single bonds to then the other atoms. So you're going to have one carbon oxygen single bond, and then a second carbon oxygen single bond. And so you're going to do that. And you're going to then get something, once I fix it, looks like almost. You're going to get something that looks like this. Okay. So you start off with your carbon in the center, and then it's going to be single bonded to an oxygen atom, and then single bonded to then another oxygen atom. Okay. So as we look at this here, we notice that Carbon does not have an octet because it has 2 and 4 electrons associated with it. Okay. And you also notice oxygen does not have an octet associated with it. So the next thing we're going to do in our procedure here is we're going to then get these atoms up to an octet by adding lone pairs. And one thing I just want to point out to you is I'm going to stick to this method, and it lets you arrive at an incorrect answer, but it's a systematic way that helps sort of analyze what you're looking at, and so I find it helpful. And so you just notice that oxygen needs an octet. So we need to add 1, 2, 3 lone pairs. And then for the other oxygen, we got to add 1, 2, 3 lone pairs. And then for carbon, it has only 2 and 4 electrons from the single bonds, so it then needs 2 lone pairs associated with it. Okay. So now what we've done is we have carbon with an octet, and then we have oxygen and oxygen both with an octet. Okay, so that is good. Um, but what we want to do here is we got to make sure that we match up to that number of 16 electrons. And so what you notice here is when you add all the electrons up, we get 2, 4, 6, 8, 10, 12, 14, 16, 18, and 20. Okay, so we are sitting at 20 electrons, and this is not good. We're unhappy with this. Okay, and so what this means is we are using too many electrons. And so we need to somehow use less electrons, but still satisfy the octet rule where it belongs. So the way we're going to do that is we are going to subtract or remove 2 electrons from oxygen, 2 electrons removed from carbon. And then what we're going to do is we are going to then add what's called a double bond between the carbon and the oxygen. Okay. And so you get something that looks like this. So what I've done here is I've taken away a lone pair from oxygen, I've taken away a lone pair from carbon, and then I have then put between them the sharing of 2 electrons. And that extra shared is what we then call the double bond. So as written here, carbon and oxygen have a double bond where they are sharing a total of 4 electrons that count up the double bond because each line counts as 2 electrons. And so if we do the octet for oxygen, we see it has 2, 4, and then 6 and 8 from the double bond. If we look at carbon, we see we has 2, 4, 6, and 8 from the double bond. Okay, so we have an octet on oxygen, we have an octet on carbon. This is good. Now let's count up the number of electrons we have. Well, we have 2, 4, 6, 8, 10, 11, 12, 13, 14 from the double bond, 15, 16, 17, 18. Okay, so we have 18 electrons here. So you'll notice that we still have an incorrect answer, but we moved it closer in the right direction. You notice that we went from 20 down to 18. And essentially, the reason our net number of electrons went down by 2 was we subtracted a lone pair off oxygen and a lone pair off carbon, and then we then added a double bond in between the 2 atoms. So we've subtracted 4 electrons and then added 2 electrons, which is a net loss of 2 electrons. So the summary statement here is for every additional bond or like double bond that you add, it's going to then cut down your number of electrons by 2. Okay. And so since we see that we're sitting at 18 and we want to get to 16, we should probably do the same thing on the other oxygen atom and carbon atom too. So what we're going to do here is we're going to then take away 2 electrons from oxygen, take away 2 electrons from carbon, and then we're going to then replace a double bond in the center. And then you get something that looks like this. And then because I like things looking the same, I'm just going to delete that lone pair and plug it up on the top. Okay, plug it up on the top. There you go. All right, cool. So this is in our Lewis structure that we have. Okay. And so you'll notice that oxygen has an octet because it has two, four, and then six and eight from the double bond. And it's the same thing for the other oxygen. It has two, four, six, and eight from the double bond. And then if we look at carbon to see if it has an octet, we see it has two and four from the first double bond, and then six and eight from the second double bond. And so then carbon has an octet, oxygen has an octet. Now we got to go back because we messed things up. We got to double check our number to see if it adds up to the 16. And so now we got to add it up. And so we see that we have two, four, and then six and eight from the double bond. And then we then go from 10 to 12 with the second double bond. And then we then go to then 14 and 16 with then max, which then now matches to the 16 electrons that we have. And this is the correct Lewis structure for carbon dioxide. Okay, so you notice that every atom has an octet that needs one, and then the total number of electrons that we're using are 16. Okay, and then one thing I do want to just point out to you, I know I was erasing the number of lone pairs. So if I were to, remove this lone pair here and then put it down here, that's also fine. So it's not like where you draw the electrons is more correct at this particular point in the class. As long as you have the correct number of bonding and lone pair electrons on the atom, then you're in good shape. Okay. All right, so that is going to be the completed Lewis structure for carbon dioxide. And the one I decided to draw for the solution, I decided to draw it this way. And so this is going to be our completed Lewis structure for CO2. Now what we're going to do is we're going to then do the Lewis structure for HCN or hydrogen cyanide. Okay. So for HCN, we'll get that going. We'll clean up what we have here. So we're going to have hydrogen, we're going to have carbon. Okay. And then we're going to then have nitrogen, and we're going to then do HCN. Delete this, and then we're going to. Cool. Okay, so we are going to be doing hydrogen cyanide. So just take a moment to look at the periodic table. We notice that hydrogen is in column number one, carbon is in column number one, two, three, four, and then nitrogen is in column number five. So when we do our math on this, we have one hydrogen atom, which brings one valence electron to the party, which gives us then one valence electron from hydrogen. We have one carbon atom, which brings four electrons to the party. Um, and so therefore, carbon brings four electrons. Okay. And then finally, we have one nitrogen atom, which then brings five electrons to the party because that's in the fifth column of the periodic table. And so then nitrogen brings then five valence electrons. And if we then add all these numbers together, we get one plus four, which is five, plus another five, which is going to then give us a total of 10 valence electrons. So for our structure that we have here, we need to use a total of 10 valence electrons for hydrogen cyanide. So what we're going to do here, we're going to follow the same outline that we did in the previous question. So you'll notice here that we only have one hydrogen, one carbon, one nitrogen, and so we have one of each of them. Carbon tends to like to form multiple bonds, so that's an indicator for carbon being the central atom. The other thing to point out to you is when people write a molecular formula, they're going to try to communicate as much information as they can with the molecular formula. And so what that means is the order of the atoms we have here is going to follow the same order that we have for then the actual molecule itself. Okay. And so we'll do the H, put the H in here. So because the molecular formula is written out as HCN, perhaps I should write the order of the atoms as HCN as well. Okay. So that's that part. So we look at this and okay, we form single bonds to the central atom, and then we got to make sure everything has an octet. So you notice, let's start with hydrogen actually. So hydrogen needs a duet, and it already has it because it has the two electrons. Carbon does not have an octet. It only has two and four electrons on it. So we gotta then do six and eight. And then nitrogen only has two electrons on it as written. So we got to start with the two electrons from the single bond. And then we got to add one, two, three lone pairs on the nitrogen. So once you do this, you then have a total of eight electrons on nitrogen. You then have a total of then four electrons on carbon and then two electrons on hydrogen. And so if we add all that up, we get the 2, 4, 6, 8, and then we then have the 10, 12, and then the 13, 14. So right now we are using a total of 14 valence electrons. And this means we are using too many electrons. And so what this tells us is I'm going to have either a double or triple bond in my structure. So yes, we got to an incorrect answer here, but because we see we have 14 compared to the 10, we know that this is what tells you you're going to have double or triple bonds in your answer. Okay. And so we're going to do the same thing. So we'll do what we did in the last question, which is take away a lone pair off both atoms, replace it with then a double bond. Okay. And so once we clean that up, you're going to then get something that looks like this. Okay. And if you count up the number of electrons, you get 2, 4, 6, 8, 10, and 12. So you get 12 electrons, um, and that still is not good. And so this means we need to then add an additional bond. And so hydrogen can only have one bond to carbon. So that means we're going to then take away a lone pair from this carbon and take away a lone pair from that nitrogen. And then what we're going to do is we're going to then replace that with then what we call then a triple bond. Okay. And when we do that, let's count the numbers. Let's see if we have an octet on everything. So hydrogen has the duet. That's good. We see carbon has 2, 4, 6, 8 from the triple bond. So carbon has an octet. And then nitrogen has 2, 4, 6 from the triple bond and then goes up to 8 with the lone pair of electrons. So when we do this, we then see that we now have a total of, let's count these out. We have a total of 1, 2 electrons from the single bond. We then have 6 electrons from the triple bond, and then another 2 from the lone pair. So we have 2 plus 6, which is 8, plus 2 gives us then a total of 10 electrons. And that is good. And so we then put the smiley face and we're good on this. So what we've done now is we take a look here is we have a duet on hydrogen. We have an octet on carbon. We have an octet on nitrogen. And we use the total of 10 electrons. And so because we have satisfied all the different rules that we have here, this is the correct Lewis structure for hydrogen cyanide. So in the format that I recommend you do, draw single bonds to the center atom, give everything an octet with lone pairs, and then if the number of electrons you're using exceeds the number that you're supposed to, that means you're going to need to add either double bonds or triple bonds. Okay. And so if one double bond counts the number of electrons down by 2, one triple bond counts the number of electrons down by 4. Or like in the case of carbon dioxide, two double bonds will also be a way to lower the number of electrons by 4. Okay, so here we've shown with carbon dioxide, two double bonds. Here we've shown with hydrogen cyanide, one triple bond. Okay. And so those are the examples of essentially what we've discussed so far here. And so we've discussed at this point now, we've discussed neutral molecules, we've discussed cations, we've discussed anions, and we've discussed molecules that are going to then either have double bonds or triple bonds or single bonds in them. Okay, so we've covered a good variety of the different types of molecules that we can work with here. And so because there's not infinite time in the world, I have shown for you here some additional practice questions that you could do. So you could do the Lewis structures for the following molecules and ion. And so those are great practice to work on. And so I'd recommend doing that. And I believe your textbook does give you the solutions to these questions. And so I would recommend work on these questions on your own, and then you can then double check them to what the book is doing. But the book organizes it in the same manner. So if you take a look at like for example the first one, which is HF, it does the total number of valence electrons, draws the single bonds, shows you then okay, well I need to I only have two electrons shown, so there's six other ones I gotta fill in. Do that within getting up to your octet rule and then check to make sure that the duet rule satisfies for hydrogen and that the octet rule satisfies for then the fluorine atom. Okay, so I'd recommend work on these questions and then double check them with what you have here. And then if you have questions, I'm happy to discuss that in office hours. Okay. All right, so there is one other thing that your book will talk about, and I want to mention it in passing here. So if you take a look at boron, okay, or in the molecule boron trifluoride or BF3, this is going to be the correct Lewis structure for boron trifluoride, okay? So you'll notice here that boron does not have a complete octet. It has two, four, six electrons associated with it, okay? And then you'll notice the fluorine atoms do have one, two, three, four, five, six, seven, eight electrons associated with them. Okay. And so what this is telling you is that boron is electron deficient and therefore it is reactive. And so this is the correct Lewis structure for boron trifluoride. Um, so if you take a look here at the periodic table, you notice that we have three fluorine atoms, and each fluorine brings seven electrons to the party. Okay. And so we have seven, so we have three fluorine atoms, each which brings seven electrons to the party. So I'll just write it out. So if you have BF3, okay. I'll get rid of these things over here. Okay. Okay. So fluorine, you have three fluorine atoms, and each fluorine atom brings seven electrons to the party, which means you're going to then have a total of 21 valence electrons from fluorine. If you look up boron on the periodic table, you know it's boron is in column one, two, and three. And so boron wants then three valence. So we have one boron. It has three valence electrons. And so boron is going to bring to the party three valence electrons. And so then if you do 21 plus 3, that then brings you a total of 24 valence electrons. Okay. And so then if you go to the Lewis structure of boron trifluoride, you then get two, four, six, eight electrons on this fluorine. And then you have eight plus another eight, which then gives you 16, plus another eight over here, which then gives you 24. So fluorine follows the octet rule. Boron does not, in this case, follow the octet rule. But you'll notice the correct number of electrons that we use does match up to the 24 that we have. So another quote unquote exception to the octet rule is boron. And as you can see, it's electron deficient. And because it's electron deficient, therefore it's going to then be reactive. Okay, so that's one exception to the octet rule. So this is us actually going under the number of eight. So that's one thing I want to talk about. Another thing worth discussing is what we will call an expanded octet. Okay, and so an expanded octet works like this. So for third row elements and below, some atoms may exceed the octet rule and can have up to 18 electrons due to the five empty d orbitals. Okay, so what does this mean for us? Here, if you take a look at SF6 or sulfur hexafluoride, you'll notice you have sulfur in the center, and then you then have it bonded to one, two, three, four, five, six fluorine atoms. Okay, and so what you notice here is every fluorine has an octet associated with it. That is good. I will also tell you that if you add up all the electrons shown in SF6, it adds up to the total that you get when you add it up from the periodic table. So we're using the correct number of valence electrons, and fluorine has an octet in every case where we see it. But the only thing that sort of looks a little puzzling here is we notice that sulfur does not have eight electrons on it. If we look at this, we see it has two, four, six, 8, 10, and 12 electrons on it. Okay. So sulfur has what's then called an expanded octet. Okay. But because sulfur is in the third row or below, we can have expanded octets. And so what this means for you is you can go up to 18 electrons once you start with the third row of the periodic table. So we'll spend a moment explaining this. So you may ask, okay, well, why the heck does oxygen have an octet? Well, the reason oxygen has an octet is oxygen has the 2s. So I know this is showing a 3s here. So oxygen has 2s and 2p orbitals. Okay, so oxygen, you'll notice, is going to be one row up. And so oxygen has the 2s electrons. So it has the helium for the noble gas configuration. And then it then has the 2s2, and then it then has then the 2p, 1, 2, 3, 4. Okay. So oxygen has a 2s orbital and a 2p orbital. You'll notice with the s and the p orbitals that you can jam in two electrons per orbital. And so if you do the s and the p, you get 2, 4, 6, 8 electrons maximum you can put in between the s orbitals and the p orbitals. Okay. However, when you get to the n equals 3 quantum number, that then means that you can now then get L is equal to 2. Okay. And when L is equal to 2, that means you can then have five different orientations, which is the -2, -1, 0, 1, and 2. Those five different orientations are going to correspond to the five different p orbitals you have. So when you have SF6, sulfur does have d orbitals, just they are empty. Okay, so sulfur does have d orbitals because sulfur has the principal quantum number of 3. So it does have these empty d orbitals. And just as oxygen, you can jam in 8 electrons where 2 go into the s orbital and then 6 go into the p orbitals. Once you have the d orbitals available, you can plug in another 2, 4, 6, 8, and 10 electrons into those d orbitals. So that explains why then sulfur can have up to 18 electrons, because if you fill up the s, the p, and the d orbitals, you can jam in up to 18 for that. So the fact that we have 2, 4, 6, 8, 10, and 12 electrons associated with our sulfur atom, that is fine because as long as we don't go over 18, we will be in good shape. Okay. And so that's one other thing to point out to you. And so as a strategy for solving these questions, I recommend, go with the octet rule for most things. And then if you notice that you aren't using enough electrons, then you can start possibly putting extra lone pairs on the atom that is in the third row or higher. Or like in this case here, you got to have all of them form a bond to it. And so don't be alarmed if you exceed the octet for a element that is in the third row or below. So in summary, hydrogen follows the duet rule. Most other atoms will follow the octet rule. And then boron will be less than the octet rule for the reasons we've discussed. And then once you're in the third row of the periodic table or lower, do not be alarmed if you have more than 8 electrons. So that's essentially the sort of whole characterization of what we have here. All right, so now what we're going to do is we are going to then draw the Lewis structure for phosphorus pentachloride, or PCl5. So we'll write it here, PCl5. Okay. And so we have phosphorus, Cl. Okay. So phosphorus, we have one of them. And what column of the periodic table is phosphorus in? Phosphorus is in the one, two, three, four, fifth column. So phosphorus is in the fifth column. And so phosphorus brings 5 valence electrons to the party, which then gives us a total of 5 valence electrons. And then chlorine, we have a total of 5 chlorine atoms. And chlorine is in the seventh column of the periodic table. So it's in column one, two, three, four, five, six, seven. There's our chlorine. And so each chlorine atom is going to bring 7 electrons to the party. 7 times 5 is then going to then be 35. And there we go. Okay, so we have 5 valence electrons from phosphorus. We have 35 valence electrons from chlorine. In total, that gives us now then 40 valence electrons for PCl5. Okay, so what we're going to do here is we need to start with assigning the central atom. We have one phosphorus, so that's a good indicator. We should start with phosphorus. Also, one other thing worth noting is the halogens, like chlorine, fluorine, they're like hydrogen where they tend to like to form one bond. Okay. And so that's another thing too, is that usually the halogens you'll just see forming one bond. Um, and so what we'll do here is we will do 5 attachments. So we will do one, two, three, four, and five. Okay. So we'll do 5 attachments to phosphorus. Okay. And then what we'll do is we'll then put the chlorines at the ends of those. So we're going to have all single bonds to the central atom per like what we've done before. So we're going to do that. And then we get something that looks like this. And then we need to make sure each chlorine has an octet. And so it has 2 electrons from the phosphorus chlorine bond. And so we have 2 electrons from the single bond. So that means we need to add in one, two, 3 lone pairs to give us a total of 8 electrons on the chlorine atom. And so we do that here. One, two, 3 lone pairs. One, two, 3 lone pairs. One, two, and 3 lone pairs. And then we here do one, two, and 3 lone pairs. Okay? And so I think what I will do is I will delete the lone pair down here and I will draw them to go down. I guess that's why the computer drew it on off to the side. So I guess I'll put it up here a little bit. All right, so those are the different electrons that we have. And so now what we need to do is we need to then check to see if we have an octet on everything. So chlorine, every chlorine atom has an octet, and that's good. If we take a look at phosphorus, we notice it has a total of 2, 4, 6, 8, 10 electrons. So here phosphorus has an expanded octet. And so remember, phosphorus is in the one, two, third row of the periodic table, which means it can have an expanded octet, which means it can go up to 18 electrons. So the fact that we're putting 10 electrons on the phosphorus or associated with the phosphorus, that is fine. And so we are good here. And so if we go back here, then we just need to double check to make sure that so we have an expanded octet on phosphorus. That's good. We have a full octet on chlorine. That is good. Now we just need to check to make sure that we're using 40 electrons in total. And so if you count here, you notice that we have 2, 4, 6, 8 electrons from chlorine. And then we then have another 8 over here. And so we have 8, 16, 24, and then we then have 32 from here, and then we then get brought up to 40 with the fifth chlorine atom. And so this is the good, correct Lewis structure for phosphorus pentachloride. You'll notice that chlorine has an octet, phosphorus has 10 electrons, which is perfectly good. And then we're using the total number of 40 valence electrons. So this is a good Lewis structure. Okay, so this is an example sort of showing when you can have an expanded octet. Okay, so that concludes that question. And so this is the solution I have shown for you. The geometry, we'll talk about geometry later in this chapter, but that's this is actually most correctly depicting the geometry, so that's why it has this sort of shape to it. Um, Now what we're gonna do is we're gonna then do the Lewis structure for I3 minus. Okay, so for I3 minus. And so let's go over here and clean up our little sandbox we got going on. So we have I or iodide or iodine, sorry, iodine. And so what we're gonna do here is, or rather iodine. Sorry, it's called iodine. Iodine versus iodide, they sound very similar, but iodine is neutral. Iodide is I minus. So we have iodine. We're gonna have three of them, and so iodine is a halogen, which is right here. So it's in the seventh column of the periodic table. And so we're gonna then have, let me get this cleaned up. So it's I3 minus. Okay, so what we got here is we have three iodine atoms. And since iodine is in the seventh column of the periodic table, it brings 7 valence electrons to the party, which means it's going to then have a total of 21 valence electrons. Okay? Then what we're going to do is we then remember it's I3 minus. So that means we are going to then add one additional electron. Okay? I'm going to add one additional electron here. And so what that does for you is you then have the 21 electrons from the iodine atoms. You then add one extra electron because it's I3 minus, it's an anion. And so what that's going to do for you is give you a total of 22 valence electrons to use for this question. And so we can get started. And so here we just have three atoms. And so I3 minus, it's all the same atom, or we only have one atom we're using here. So we're going to do I and I and I. So we're going to put an iodine here, and then we're gonna put an iodine here, And then we're gonna keep the iodine here. One pro tip I can give you, usually, so like I like writing out my Lewis structures using Arial font. But the downside of using an Arial font with iodine is that the I looks the same as an L, so it can get confused possibly as an L or like chlorine. It gets confusing for people. And so, in general, you want to make sure that when you have your IDs written out, you want to do it in Times New Roman just to make it more obvious that that's the atom you're talking about. So that's a pro tip I give you. It makes the interpretation and reading easier for people and less ambiguous. Okay, so we have three iodine atoms, and we need to then we have iodine being the center atom and the other two being attached to the center atom. So now what we need to do is we need to then get a full octet on each of these things. And so we have two electrons on this iodine from the single bond. So we need to add one, two, three um, lone pairs to it. This one on the right-hand side is in the same circumstance, and so we want to then add one, two, three lone pairs to then the iodine on the right-hand side. And so therefore, both the left and right iodide have one single bond and then three lone pairs, which gives you a total of eight valence electrons on this iodine and this iodine. And then we notice that this iodine in the center has two and four electrons from the single bonds, which means we then need to add one and two lone pairs to then the central iodine atom. Okay, so now we know that each iodine is going to then have um, total of eight electrons on it, and so the iodine is going to then have then a full octet. And so then what we do is if we want to then add these up together, we can then see that we get 2, 4, 6, 8, 10, 12, 13, 14, 15, 16, 17, 18, 19, 20 electrons. Okay. So we are showing here 20 electrons, and we need to use 22 from the math that we've done. Okay. And so what this means is we need to then add another two electrons. But the thing here is iodine. It's gonna then it's in the third column or higher. So we notice it's all the way down here or sorry, it's in the fifth row. So this can definitely have an expanded octet. And so in general, when you do an expanded octet, at least in the introductory example, it tends to be that they put the extra lone pair on the central atom. And so I'll move these over here a little bit. And so I think I'll just delete these two and draw them out. So we'll put two here and then we'll put the there. So we'll make it look like this. Okay. And so now what you'll notice is this iodine is going to then have eight electrons. This iodine is going to then have eight electrons. And then this iodine here is going to have two, four, six, eight, and 10 electrons on it. So it's going to have an expanded octet, but that is all good because it can have an expanded octet. And then we then just double check to make sure we're using the correct number of electrons. And here we have 2, 4, 6, 8, 10, 12, 14, 16, 17, 18, 19, 20, 21, 22. So here we then have that. And then remember, it's I3 minus. So we're going to then put brackets around it. And then we're going to then put the little negative charge up on the side. And then we are good. And so this is going to be the correct Lewis structure for I3 minus. Okay. And so solution is going to then look maybe something like this. Okay. All right, let's see where we are. All right, so we got a couple more slides left to do. Okay, so that concludes essentially discussing how to draw Lewis structures for a variety of molecules and ions. Okay. Um, Now what we're gonna do is we'll spend a couple slides on this, and then we will then conclude our lecture shortly. But the next sort of major topic that we're going to introduce is something called a resonance structure or a resonance contributor. Resonance structures or resonance contributors, they're important, and especially if you take organic chemistry, they're very important for that class. You'll get lots of practice and get really good at it in that class. So here I want to introduce to you what it is, what it looks like, and I want to talk about it a little bit. So essentially, a resonance structure or contributor is invoked when more than one valid Lewis structure can be written for a particular molecule. Um, and so what you get is the resulting electron structures of the molecule is then given by the average of these resonance structures. So, for example, if you look at NO3 minus, if you were to draw the Lewis structure for NO3 minus, you would get something that could look like this. Okay. You have nitrogen oxygen single bond, nitrogen oxygen single bond. Then you have one nitrogen oxygen double bond. But the question here is like, okay, well, can I put the double bond between the top oxygen? Or could I put the double bond between the bottom right oxygen? Or could I put the double bond between the bottom left oxygen? And the answer to that question is you can do all three of them. And so the question here is, well, which one is correct? And the correct answer is that the true molecule actually does not exist as either of these three, but it's going to be a sort of average of those three put together. So, in that sense, the true structure is what's then called a resonance hybrid. So, what this tells you is this double bond can go here, here, or here. In actuality, it's going to be distributed across all those locations at the same time, and the true molecule is going to look something that's considered a weighted average of these three structures. And so the experimental molecule is going to only have, one given set of bond lengths, but it's going to be influenced by these particular resonance contributors. Um, and so another way of saying that is that resonance contributors are one of a set of Lewis structures that differ only in the distribution of electrons in covalent bonds and lone pairs. So for example, if we have CO3 2 minus, you'll notice that you could have a single bond, and a double bond. And that double bond could either go up here, down here, or down here. Okay. And so, because those are three equally valid good Lewis structures, each one of these structures is going to contribute roughly 1/3 to the true experimental structure of the carbonate anion. Okay. And so you'll notice when you're doing the Lewis structures, you're not changing any of the order of the atoms. You're just changing where the electrons are. And so this double bond pair of electrons is going to either be here, here, or here. Later on in the class, we'll talk about this thing called a pi electron, and pi electrons are the ones that can actually move. But for now, we'll just take a look at it as the valence electrons. And so that's another example of a molecule that then has multiple resonance contributors. And so the question here is like, if you were to look at like, for example, this carbon and this oxygen, here it's shown as a single bond, but here it's shown as a double bond. But then here it's shown as a single bond, and here it's shown as a double bond. So the question is the carbon oxygen, the one going up in the center, is it a single bond or is it a double bond? Well, 2/3 of the time we're showing it as a single bond. 1/3 of the time we're showing it as a double bond. So it turns out that it's going to have a bond length that is similar to that of a single bond, but it's going to be a little bit shorter because 1/3 of the time it's going to have double bond character. And it's going to be the same thing for then this oxygen here, and then this oxygen here. So it turns out that the carbon oxygen bond lengths will be somewhere in between that of a single bond and a double bond. And all three carbon oxygen bonds will then have the same bond length because each one of them is going to have two contributions of single bond and one contribution of double bond. So, in short, the true structure is going to be the weighted average of the different resonance contributors. And since these resonance contributors are all equally good, and we'll talk about what that means in the next sort of set of lecture slides, they're going to get equal weight. And so it's going to be an equal weighted average for this. Okay, so that concludes this question, and I think this is yeah. So it can just say here that the symmetry of each resonance contributor is going to be considered weighted equally due to the symmetry. Okay. And then I think this is going to be then the last, this is going to be the slide that we'll pick up with for then the next class that we do. And so, in summary, what we have talked about today is we have talked about how to draw a Lewis structure. You start with the molecular formula, you then get the number of valence electrons, you then figure out the central atom, you then bond all the other atoms to the central atom. And then if they don't have octets, and they should have octets, add lone pairs to them. And just remember, hydrogen has a duet. Most atoms will have an octet, but if your atom is in the third row of the periodic table or lower, it's going to then have an expanded octet. So don't be alarmed if it goes anywhere up to 18 electrons. So we did a lot of Lewis structure analysis today. And then we got introduction to this whole thing of resonance contributors. So I want to show to you that they do exist, and we explained a little bit about the physical significance. And then we're gonna then dig into that more when we then go into the next set of class lectures. All right, thank you, and have a great rest of your day. Thank you.